So the whole big box of query parsing and optimization can be broken down into pieces, and let's go through those pieces right now. We start with some input, which is an SQL query up in the upper left here. It's passed into a query parser. That query parser turns the syntax of the query into some abstract syntax tree, internal representation of the text, and passes it to a query rewriter that puts the query into canonical form. That query rewriter then passes the rewritten abstract syntax tree into the query optimizer. And it's the job of the query optimizer now to turn that abstract representation of the query into an efficient plan. And so the query optimizer has a piece to generate alternative plans and a piece to estimate the cost of each plan, because we're going to want to pick the generated plan that seems to be the cheapest. That plan cost estimator is going to look at the catalog manager of the database to get statistics about the different tables in the query to help compute what the costs are. And the plan generator is going to use the catalog manager to get the schemas of the tables to figure out exactly what's a legal query plan and what's not. Once the query optimizer has chosen an optimal plan, it passes it to the query executor, which then executes the plan in the way we've seen before, using iterators and relational operators. So in a little bit more detail, what's the job of the query parser? Well, it's going to check the correctness of the query. It's also going to check that the tables that are referenced in the query are tables that are authorized to the user to be seen. So it does a little bit of authorization checking as well as just straightforward language parsing. It does generate an internal abstract syntax tree, sometimes called a parse tree. And really, there's nothing special about an SQL query parser. It's like any other parser for any language. So it's fairly straightforward. And if you haven't learned about parsers, I encourage you to learn about them, but we're not going to cover that topic in this class. You can just assume that it takes SQL text and it generates some abstract representation of that text in memory. The query rewriter is an interesting component. It converts the query to some internal canonical form. So it'll do things like take views and incorporate them into the query. So if you have a view with 3 tables in it, and then you have a query that joins that view to another table, the query rewriter will flatten that into a 4-way or a 4-table query with no views. So it flattens the views. Sometimes it can convert subqueries into joins similarly, so it converts subqueries into fewer query blocks. It's doing whatever it can to make the query look like a very simple relational algebra query of selects, projects, and joins. And that can be tricky in SQL when you have subqueries and common table expressions and views and so on. I will say that query rewriters in commercial databases can be pretty sophisticated, but in most of the open source databases, even advanced open source databases like Postgres, this is a bit of a weak spot. So there are often cases where a query over a view or a query with subqueries won't get flattened into joins as well in Postgres as it might in a commercial system. So it's just something to keep in mind. We won't learn a great deal about query rewriting in this class. It's just something you should know about, so I bring it up here. What we are going to spend most of our time on in this class is what's called the cost-based query optimizer, which takes queries one query block at a time, where a query block is a bunch of select, project, join operators with a group by aggregate and an order by on top. Okay, so it's just that construct, and it gets one of those at a time, and it's going to optimize each of those. If you have subqueries, the subqueries will get optimized independently. The cost-based optimizer is going to use the catalog statistics to find a least cost plan per query block. We'll see how that's done in the course of the next 2 lectures. And, some people would say that the query optimizer is in some sense the soft underbelly of any database management system because it's not really truly optimal. And we'll see reasons for that as we go. It's going to hopefully do a good job picking a good query plan for your query, but sometimes it doesn't. And people who are used to controlling their software tightly, people who like to do their engineering themselves, sometimes get frustrated with query optimizers because they're not perfect, and occasionally they make mistakes. So it's something to know. And as we go through our slides on query optimization, keep an eye open for places where heuristics are being used or there's inaccuracy in estimation. And those are places where the query optimizer might need to be improved. Okay, so the overview of the cost-based optimizer, of the core of query optimization, you can think of like this. The query block can be converted into a relational algebra set representation, right, which is like a tree, as we saw before. And then in that tree, each operator has some implementation choices. For instance, a join operator can be implemented with one of a number of join algorithms. Also, as we know, the operators can be applied in different orders, and we'll talk about that quite a bit. So we can reorder the tree in different ways, right? The core of query optimization consists of three components that are beautifully orthogonal. Each one of these concerns is separate from the other, which means that we can innovate and improve each of these concerns independently. And as we get better at one, it doesn't affect our decisions on the other. So the first of these three concerns is our consideration of what is the space of plans that we're going to search. What are all the different possible ways to implement this query? And then once we enumerate all the possible ways we can implement it, we choose among them. So that plan space can be very large, and by introducing, for example, new join algorithms or new ways to combine operators, we can increase that plan space. The second concern is cost estimation. If we have a particular plan that we're thinking might be a good one for this query, how do we estimate the cost of that plan? How can we figure out how long we think it'll actually take to run? Because, of course, what we're going to want to do is pick the plan that we think is going to be the fastest to run and then run it. And then our third concern is a search strategy. Given that we have this big plan space, and given that we can estimate the cost of each plan, how do we efficiently find the plan with the cheapest cost estimate in that plan space? So those are the three pieces of query optimization, and we're going to look through them one by one as we go through this next sequence of lectures. The goal in query optimization in the end is to find the plan with truly the least actual cost, the one that will run the fastest. The reality is that we're going to find the plan with the least estimated cost based on our cost model. Our cost model might not be entirely accurate. As we will see in subsequent lectures, it's going to have to make some heuristic approximations to reality. But overall, what we're really trying to do with query optimization is avoid really bad plans and pick plans that in reality work pretty well. And we'll see that because plans can vary enormously in their performance, some can take weeks where others would take seconds. The most important thing for us is to avoid the really bad plans and get into the regime of the good plans. Maybe not the very best, but one of the good plans usually suffices.